is just going to have to be an implicit solution, okay? But an implicit solution is better than no solution, okay? All right, so in the time that's left, let me just sort of sketch out the general method of characteristics, okay? In R2, okay? Where I just mean, you know, you have two independent variables, okay? So in general, okay, what this is going to look like for what's called a quasi-linear PDE, okay, is that you may have some coefficients on your one of your derivatives, okay? You may have coefficients on one of your other derivatives, okay? And I'm going to make the independent variables x and y in this case. It could be x of t, okay? X and t. And your right-hand side could be any nonlinear function, potentially, of x, y, and u, okay? And your initial data, okay, we'll allow that to be pretty general. It's going to be u is equal to some function z0 of s, okay, on this region I'll call gamma, which can be a parametric curve of x and y, okay? So it doesn't have to be a nice, you know, sharp boundary like this. It could be some curved boundary, okay? That's all this allows us to do, okay? A few more caveats, okay? A, B, and C are going to be C1 functions, okay? X0, Y0, and Z0, okay, are going to be C1 functions, okay? And S is going to be defined on some subinterval of R, okay? And then there's going to be some surface, okay? That's our initial surface, gamma, x, y, z, okay? X equals x0, y equals y0, z equals z0, okay? This is our like initial curve, okay? Now, what we want to reveal, okay, by kind of breaking this down is that we can take this PDE and turn it into a set of ODEs, okay? So if U, okay, is a solution to our boundary value problem, okay, or we could call it an initial boundary value problem, Z equals U of X, okay, is a surface in X, Y, and Z, okay? So I'm gonna try and draw this surface now, okay? The idea is that we have Z, okay, this is our like vertical dimension. We have X and Y, and we have some initial data here. This is that capital gamma that I drew there. And as you move along this, okay, you're moving in this variable S. This is your parameterizer of your initial curve S, okay? And there's another variable, I'll call it tau, okay? That's sort of like the other part of this new coordinate system that we're gonna map to in order to go from a PDE to an ODE. And what happens, okay, is that taking some initial point on this curve, solutions are gonna sort of emanate from your initial data to kind of trace out this surface, okay? So all of these points along the initial curve, they have tau equals 0. And as you move along them, you're increasing tau, okay? So the idea is that if I stay along one of these curves, okay, I should have the same, and like, I should have the same profile as my initial value. So moving along it, it should just sort of warp my initial data, okay? But it's really just going to sort of translate it forwards in this, along this surface. So this creates this surface Z. Z equals U of xt. That's how I trace my surface out, okay? And we'd like to be able to say, well, how is it that you kind of move along this surface, okay? In a way that's related to the ingredients of the problem, A, B, and C, okay? Well, the vector A, B, C, okay, is going to be tangent to the surface Z equals UXY. And the reason that this is because the function U of xy minus z, okay, where that thing, when that's equal to 0, that's essentially our solution surface. If you take the gradient of this, you get the vector ux, uy, and minus 1, okay? So ABC dotted with this gradient, u of xy minus z, okay, is going to be equal to a ux plus b uy minus c, okay? And we know that that's equal to 0. Why do we know that's equal to 0? Well, because that's just a rearrangement of this PDE up here, okay? So this gradient here, okay, and this vector here are orthogonal to each other, okay? So they sort of form the vector that determines the flow along this surface, okay? And the normal to this surface at any particular point, okay? So this normal here is ux, uy minus 1, okay? Well, so what? Well, if you remember back to our transport equation example, okay, we created our characteristics, okay, so that when we dotted the different sort of independent variables derivatives with the derivative terms with respect to our unknown function, that would all be equal to 0. We're going to try and do that same thing here, okay? So the idea is that we want to parameterize our surface first by these new variables s and t, and x is going to be some function of s and tau. Y is going to be some function of s and tau. And z is going to be some function of s and tau, okay? And we can then take, if we can then write down the ODEs for x, y, and z in this case, okay, we'll have their initial conditions for any particular value of s, okay? But then the only thing that we need to worry about is how they're changing along each of these individual characteristics, okay? So we no longer have to solve a full PDE, but just along each of these characteristics, as we move along tau, we need to solve an ODE just with respect to the variable tau, okay? So we're taking this two-dimensional surface and we're breaking it up into an infinite number of these strings that are kind of emanating from this initial parameterized curve. And that's what our ODEs are. They live on these strings, on these now one-dimensional domains, okay? So once we solve for those, we can recover u of x, y by inverting x equals x of s tau, and y equals y of s tau. Okay, and what is it that allows us to do this? Well, it would be the inverse function theorem. And if you remember back at the beginning of the lecture, okay, in order for the inverse function theorem to work, okay, we need to have an implicit description of our function that's invertible. So there's going to be some condition that we need to satisfy in order to, be able to solve this for to be able to do this inversion. Okay. Now, this is just supposed to give you some intuition for how method of characteristics works. I have not yet written down that method, okay? So I have about like 3 minutes left where I can sort of start writing these things down, okay? But I want to pause now and just ask, is there any questions for this sort of intuition behind the method that we're about to talk about? We'll probably have to go through it on Wednesday, basically.
In higher dimensional spaces, is it essentially the same, but instead of parameterizing with the curve S, we parameterize with some hypersurface and then advance?
Yeah, exactly. Yeah. So the idea then is, let's say you did it in R3 and you had 3 independent variables, and you would have an ODE associated with each of those. And then you would have the ODE associated with your dependent function. And your initial surface now is going to be, one more dimension than before. So just like if you're on, if you're solving a problem like that has, X, Y, and time, then your initial condition needs to be in the plane rather than along the line. And then you may also have some boundary in addition to that, right? So yeah, that's the idea. Okay. All right. So I think I'm going to leave it there for the lecture today because I don't want to rush through setting it up. So know that the next step in this process really is to talk about the method of characteristics and then link it back to this picture that we have for how knowing about, the orthogonality of the total derivative, because that's what, this thing that we wrote down here, that's really in some sense the total derivative or the gradient of the operator associated with our quasi-linear PDE. This is the coefficients of our PDE. Of course, they could be functional. That's fine. There's still coefficients. And so the idea is to basically pass these coefficients off into ODEs themselves. Remember, if you go back to the transport equation example, the thing that showed up in our ODE for X was a coefficient. It was specifically the coefficient of the u sub x Okay. That same thing is going to happen here when we go to the general method of characteristics. Basically, all of the things that sit as coefficients in front of each term of your PDE are going to become right-hand sides of ODEs. And if those things are nonlinear, you're going to have nonlinear ODEs. Okay. So that's what we'll go through tomorrow. Okay. So that's all the lecture for today. See you all on Wednesday. But obviously I have office hours now, so if you want to stick around and ask questions about this or the homework, you can. So thanks. Yeah, and this is being recorded, and I'll chunk it and put it up on the web later today. Yeah.
I have a quick question.
Yes.
So in our example for the general transport equation, we said x, we parameterize x by t, but what we're really doing is just saying t is equal to s, right?
So t is equal to tau in this case.
T is equal to
yeah. So if you want to use the
using the
terminology,
general
yeah.
approach.
So you can do, we'll do an example where you see that, and you just end up with t is tau. That's usually what happens for these nonlinear wave problems, is that t is the easy one to deal with, and then x, you get some possibly complicated characteristic that's going to involve t.
Gotcha.
Yeah.
And then on the other side, like we were looking for, like we kind of define characteristics as lines along which this total derivative is 0. But we took that with respect
the total derivative dotted with your coefficients.
Dotted with your coefficients, right? But in our example, we took that with respect to time, but we could just as well have done it with respect to x and switch things.
Yeah. I mean, so the thing that was sort of hidden in that is that in our example, it worked out nice to take the total derivative instead of taking the gradient and dotting it with the coefficients. In general, you want to think of it as you're gonna take the gradient with respect to x, y, and u. And then you're gonna dot it back with the coefficients that you have.
Gotcha.
Which will basically create the operator that gives you your PDE.
Right.
Yeah, it's a good point. Thanks.
I had a question about the homework. I don't know if anyone has more questions about the lecture before.
I guess if you wouldn't mind just explaining S. So T and tau, I see how that relates. S is just likening to X, and kind of the example we did with, or like for the first half of class. Is that a good way of thinking of it? Or S?
For the example in class, it's just for your initial condition, how do you move along your initial condition? And I mean, in our case, X, you could think of X as just being S. But as you move along in T, it's still going to be in S, but then because your characteristic is some function of X and T, it's not just going to be X anymore. It's going to be X minus CU of T.
So S is just moving along the same bit, and then tau is what propagates it forward.
Exactly. Yeah. So S moves you along your initial data, and then when you move off of the initial condition, it moves you in between characteristics. Like these lines that are propagating away from the initial data. So it switches you between different characteristics.
Okay. So in the wave equation, you have X minus CT as the characteristic. But then if you picked X minus CT was 5 versus 3, that would be shifting.
Yeah,
S.
so those would be different values of S.
Okay. Okay. Thank you. That helps clear things up.
Okay, cool.